everyone, this is Karthik Chilkapati with Physics 2212 Lab 5 Magnetic Molasses. So, introduction, the purpose of this lab is that we are trying to measure the time it takes for a magnet to fall through an aluminum foil tube, and we'll be using these Faraday's laws and principles to calculate this time fall. So, physics principles, you have the Biot-Savart law, which is basically mu naught over 4 pi times qv cross r over r squared. We're going to be using Faraday's law in this case also, and then we're also going to be using the time derivative of magnetic flux, which is this big equation over here. Result was that the experimental data showed that the fall was 1.26 seconds, while the coding showed that it was 1.197 seconds. So starting off with our initial conditions, our system is basically only just our bar magnet and the aluminum foil, and the surroundings are Earth and everything around our system. Initial conditions, the tube length of the aluminum foil tube was 0.32 meters, and its radius was 0.03 meters. And the magnetic mass, or the mass of the magnet was 0.025 kilograms. And then we have our constants of gravity of 9.81 meters per second squared. We also found the resistivity online for aluminum, which is 2.65 times 10 to the negative 8 ohm meters. So experimental data, basically this was what our experimental apparatus looked like. We had this aluminum foil tube, and the bar magnet was going through the tube over here and just falling through it. And through 5 different trials, we recorded the time that it took to fall for each trial and found an average to be 1.2602 seconds. In the computational data, we basically just have some constants over here again of mu naught over pi and g, and then we input all of our tube dimensions into the code, and then we also put in our masses, our magnet's mass, and the magnetic dipole from lab 3. And then we just calculated the magnetic dipole again using our lab 3 information, and then we basically were finding the F gravity and the F magnet to find the net force acting on our magnet. And since this consists of gravity because it's falling in the magnetic field caused by the aluminum foil, and we basically found that magnetic force through this calculation over here. And then we just found the bar's velocity and position as it fell through the aluminum foil tube using typical kinematic equations. Moving on to the discussion, this was the graph that our computational data or process outputted. It's a velocity versus time graph, and we can see that it starts falling the speed was falling, or the magnet was falling with increasing speed, but then evens out to a steady speed, and then eventually just falls out the magnet. And we got the time from the computational being 1.97 seconds. And our actual timing from our experimental data, the average that we took from the 5 trials was 1.26 seconds. And I calculated the percent difference for this, and that would be about 5.28%. As always, there's error in each lab, and one error could be like when I was holding the aluminum foil tube, movement from my hand could cause the magnet to hit the walls and disturb its flow through the tube. And there could also just be any other potential human error that we are not aware of. Our what if questions: what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So if the resistivity of the conductor was 0, the force breaking the magnet would increase, and eventually the magnet would not be falling through the aluminum foil tube. And then what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? Since there are holes or slots, there's basically less aluminum foil and aluminum material helping break the magnet, so that overall magnetic force caused by the aluminum decreases. So the magnet would basically have a lower magnetic force acting on it, allowing it to fall more quickly than originally having a full solid tube. And that is it. Thank you.